In this video I'm going to show you how to draw the tangent plane to this surface. So you know in 2D y x square root of x looks like this, or in 3D it looks like this. So you've got your square root, your curve, you've got your curve like this. So in 3D it will look like this. So jump to Geogebra, punch in your surface, and we want to evaluate the we want to find the tangent plane at this particular point at A, 1, 2, 1. So we want to find the tangent plane right at this point here, right at A. Okay, so the first step is to convert our surface, our function, into this form. So currently it's of this form because you're manipulating x and y. You're manipulating x and y, and then here it spits out a z. Here it spits out a z. We want to convert this into this form here where you manipulate x, y and z, x, y and z, and then it will spit out some sort of constant. So we want to represent this in this form where it spits out a constant. And the thing is, these two are exactly the same but just written differently. So in short, we want to rewrite it in this form. So looking at this, square both sides, so that will then give us this, and then add x, that will then give us this, and then take away y, that will then give us this. So these two are exactly the same but just written differently. But then if you look at this, this is you manipulating x, y and z. This is you manipulating x, y and z. Do whatever you want on this side, and then it spits out a constant. It spits out a constant. So get into this form, and once you're in this form, work out grad f. So remember, grad f is given by this, and you should know this by now. So when you work out grad f, once you've worked out grad f gives you the ability to work out all the vectors that shoots straight out of the surface. So when you're up here, it shoots out straight out of the surface, straight out of the surface. But the thing is, you want to evaluate grad f right at this point, right at this point. So you want this, you just want this vector here. So once you've calculated grad f, so let's calculate grad f first. So calculating grad f, so looking at this, take the partial derivative with respect to x. So when you differentiate this whole thing, it gives you 1 with respect to x. So that would be 1i. So it gives you 1. And then differentiate the whole thing with respect to y. So here it would be -1, -1. And then with respect to z, so differentiate this whole thing here. So this would be 2z. So this would be 2z k hat. So grad f gives you the ability to work out all the vectors that shoot straight out of the surface, but you want the specific vector at this location. So you need to evaluate grad f at this particular point. So now put this into the x, but there is no x. Put this into the y, but there is no y. Put this into the z, and this would then become 2. So your vector is 1, -1, 2. That's the vector that shoots straight out of that surface at that particular point. So so this vector here, 1, -1, 2. So this vector that shoots straight out of the surface is actually 1, -1, 2. So let's test it in GeoGebra. So define your vector. So vector equals this. So this is our vector from the origin, but we want to move this vector to this point. So you would punch this in a, because we defined a to be that point, and then a plus u, because we defined u as being this. So anyway, move this vector to here. So now you can see that it shoots straight out of the surface. You can see that it shoots straight out of the surface. Okay, and then and then going back to here. So we found our grad f at that particular point. So once you found your grad f at a particular point, in your mind, picture this. Remember, once you've got a normal vector and a particular point, you can always come up with the equation of a plane. So picture this in your mind. This is this doesn't represent our surface, but let's just imagine this in your mind. Once you have a vector, you can always come up with the equation for the plane. So demand your general. So set up a general point x, y, and z. You demand this vector here to be at 90 degrees to your normal vector. So you demand this to be at 90 degrees. So what is the vector from A to B? Well, from A, walk back to the origin. So that would be negative 1, negative 2, negative 1. So that's you walking back to the origin, and then from the origin jump to your general point. So just imagine this point is 10, 10, 10. It's at a location 10, 10, 10. So you would just move to 10, 10, 10. But in our case, it's plus x, y, and z. So the vector from A to B is actually given by this. So you demand this purple vector to be at 90 degrees to this vector, to our normal vector. So that's how you would describe the equation of a plane. Because remember, we've done this before. The dot product of two vectors has this relationship where the angle that exists between them is given by theta. So when it's at 90 degrees, when the two vectors are at 90 degrees, cos of 90 would be 0. So this whole thing here would be 0. Well, you should already know this. So so to describe the plane, we would demand that this vector, we would demand the dot product of the two vectors to be 0. That's how you describe the plane, and we've done this, so I'm expecting you to know this. And then now compute the dot product. So it will be this times this plus this times this plus this times this equals 0. And then tidy this thing up, and it will then give you this. Punch this into Geogebra, and then it will give you your plane that is tangent at that particular point. So you can see it right there, tangent. Okay, so that's our plane. Okay, so hang on. Let me spin this. How do you spin this? There. Well, anyway, that's our plane. Okay.